would like to start by thanking the organizers for inviting me here, which is my first time both in Brazil and IMPA, and also for being here for Jair's birthday. 1 year and a half ago, many of us were at Toronto for the Marsden Memorial Workshop, and there I had the opportunity to give a talk about some work I'm doing with James Montaldi at the University of Manchester, and we are trying to study the role of continuous isotropy in the dynamics of Hamiltonian relative equilibria. And then after my talk, Tudor Ratio came and asked me if I knew about the super fast transition in the sleeping Lagrange top, which of course I didn't. And then he suggested that using our research, maybe we could try to give some explanation about this phenomenon, which was still a bit of a mystery. So then this appeared for the first time in this, I would say, already classic paper written by Luis, Ratio, Marsden, and Simon, which is the Lagrange top, or the heavy top, a geometric treatment. And there they do a lot of things in a Hamiltonian formulation for this problem. And one of them is this particular motion of eigenvalues that I will show later, and that implies, in some sense, that there should be some bifurcation going on, but it's not completely clear how to interpret these results. So after thinking about this with my student, Miquel Teixidó, at Barcelona too, we think we came with an explanation from this phenomenon that I would like to tell you today. So this is very basic. Everybody knows about the heavy top or the Lagrange top. It's this Hamiltonian system which consists in a rigid body with a fixed point and immersed in a gravitational field pointing, downwards, the gravitational field. The difference between the heavy top and the Lagrange top is a particular case for which the body is axis-symmetric, so we have this axis of symmetry. The configuration space for this Hamiltonian system is just the group of rotations, the attitude of this rigid body, and it's a simple mechanical system, meaning that the phase space is its cotangent bundle. Now, because of this axis symmetry, and because of the gravity, the group of symmetries of this system is S1 times S1. Now here, the left S1 acts on the left of the configuration or attitude space SO3, and this corresponds to the breaking of the SO3 rotational symmetry breaking by this gravitational field. And then there is a right symmetry, which is acting on the right of SO3, is this second S1, which appears because of the symmetry of this rigid body. Okay, and then this is the Lagrange top. The Hamiltonian can be written in this way, where here, in the inertia tensor, you see that there are two equal moments of inertia, meaning that this body is axisymmetric. I'm interested in relative equilibria of this system, and relative equilibria, as many people know here, are Hamiltonian solutions or Hamiltonian orbits of this system, which are also contained in group orbits for this symmetry group, meaning that there is a generator in the Lie algebra of this group, and the subgroup, uniparametric subgroup, generated by that element in the Lie algebra, applied to some point, is the same as the Hamiltonian evolution. That's relative equilibrium. So here, the two relevant relative equilibria are the sleeping Lagrange top, which is the one I'm concerned with, and the precessing Lagrange top, right? Another example of these solutions in nature that I found very recently is in this picture, where you can see here one particular case of the sleeping Lagrange top, or almost a sleeping Lagrange top in the upright position. So I want just to give a few details about the Hamiltonian formulation for this particular relative equilibrium. This point in phase space, which is a cotangent bundle of SO3, is given by the identity matrix, meaning that our rigid body is in the upright position, right, which is also the reference position. You can use another convention, but this is the usual one. And then I'm going to choose to put here some parameter lambda, and then I3, which is the third component of the inertia tensor. And for each value of lambda, this is a solution which is a relative equilibrium. Which is the generator or the angular velocity of this relative equilibrium? is, I will come later to this, is this pair, CL, CR, corresponding to the Lie algebra of G, which is a torus, S1 times S1, such that the difference between both is this number lambda. This lambda is actually the effective angular velocity, if you like, because since the body is in the upright position, the left action of the group cancels with the right action of the group, or if you want, you can think that the body is orbiting around the vertical axis, but also spinning about the symmetry axis, which is the same as the vertical axis because of this position. And then you can only talk about the difference between the angular velocity or orbital angular velocity and spinning velocity. That means that there is some ambiguity in the definition of my generator, my velocity psi, and we can make this freedom explicit if we write psi in this different way, which is lambda over 2 plus eta, comma, minus lambda over 2 plus eta, where eta, comma, eta, or eta is just a real number, and you can see that this pair eta, comma, eta belongs to the Lie algebra of GZ, which is the diagonal embedding of S1 in the torus, which is precisely the isotropy for this point in the phase space. Or if you like, the group S1 times S1 acts in a norm-free fashion in this phase space, and this particular point has as a stabilizer this group GZ. Right? So this is a case of a relative equilibrium with continuous isotropy. And that means that the freedom in choosing the representative for my angular velocity is given exactly this freedom by the size, if you like, of this isotropy group. Now, eta is arbitrary because the angular velocity only depends on the difference CL minus CR. It's completely arbitrary. And you can choose it as you like. And in the paper that I'm going to talk to you about in a few moments, there is implicitly a choice, which is eta equal lambda over 2. Because if you look at this and you choose eta in this way, then you are actually canceling the right part of this generator, meaning that you regard your body as only rotating and not spinning. But of course, this is just a choice because you cannot distinguish, right? And then I will come to this relation, eta equals lambda over 2 later. I also want to talk about the slow-fast transition, or the fast top condition, which is this classical result, already known since, I don't know, probably the 19th century, which is that if lambda, which is the effective angular velocity, is high enough, then this position, the sleeping Lagrange top, is stable. And that's what we do with these toys, the tops, when we spin them fast enough. That's satisfying the fast top condition. Okay. So this is the paper from '92 where all this is worked out. Of course, at this moment, the role of singularities or singular actions, non-free actions, and continuous stabilizers was not completely developed. But there, they observed the following phenomenon, and it's the following. First of all, you can think that your body can be represented, of course, as any rigid body by an inertia ellipsoid. In this case, this ellipsoid is going to be an spheroid. Why? Because there are two axes which are equal, right? So that means that there are two inertia values which are equal to. The body is called prolate if the different one is larger than the other two. And the body would be called oblate if, like the Earth, the different axis is shorter than the other two. In this case, what you observe doing the linearization of this sleeping Lagrange top, as you vary the angular velocity, lambda, is the following. First of all, if you start at 0 or lambda is small enough, then the system is unstable because you are not satisfying this fast top condition to make it stable, right? In that case, of course, you observe that the eigenvalues should have a non-zero real part, right? Because this system is unstable. Once you cross this particular value that I showed before, which is the classical slow-fast or fast-top condition, these eigenvalues are always in the imaginary axis. And the system is non-linearly stable in the G-mu stability sense or whatever sense you may want to think about. But now, if the body is not prolate but is oblate, meaning that it has this shape, something different happens. And what happens is that, up to this point, we have exactly the same behavior, is unstable for low velocities, and then once you get to the fast stop condition, the eigenvalues belong to the imaginary axis. But then, if you keep increasing the effective angular velocity, one pair of eigenvalues becomes 0, and there is a crossing here. This is actually implying that there should be some bifurcation. But this system is very well known, and the only things that happen here are the following. I'm going back for a little bit. So we are in the family of sleeping Lagrange stops, and if the angular velocity, or lambda, is small enough, this is the only solution. And if it's fast enough, so you are past the fast stop condition, then this equilibrium becomes stable. Before it was unstable, and then there is a bifurcation at each point of the stable range to precessing Lagrange stops. When this azimuthal angle is going to be opening slowly as you increase the angular velocity. So this is completely known. So the question is the following. Why, in the prolate case, we have this behavior that we expect, but in the oblate case, we have this 0 crossing here, right? This comes from the linearization, and what I want to show now is how I think is the best way to incorporate continuous symmetries and continuous isotropy in the linearization of symmetric Hamiltonian systems, which would explain this behavior and show that it's actually artificial and nothing special is going on here. So for that, we'll go to Blackboard. I will explain what is our approach to study local dynamics of symmetric Hamiltonian systems. So the setup will be, we have a symplectic manifold. We have a Lie group, which acts here in a Hamiltonian way, meaning that it acts by symplectomorphisms and admits, as usual, an equivariant momentum map from the symplectic manifold to the dual of the Lie algebra of my symmetry group. And then I have a Hamiltonian, which is invariant. So suppose we have a point in my symplectic manifold, or phase space, which has momentum, or angular momentum, mu, in the dual of the Lie algebra. And it has as a stabilizer the group GZ. Okay. First thing we are going to do is, as usual, compute what is called a symplectic slice, or if you like, symplectic normal space, which is the space on which you study linearization of this kind of Hamiltonian systems. And how do you define this? You do the quotient of the kernel at this point of the momentum map, the linearization of the momentum map, divided by the infinitesimal generators associated to the elements in the Lie algebra of G that fix this mu according to a coadjoint representation. So this happens to be, just by general theory, a symplectic vector space where the symplectic form is induced from this omega, and we will call it a capital omega n. Then Marl, Guillemin, and Stenberg came with this symplectic tubular neighborhood for Hamiltonian actions of symplectic manifolds, which is the following. Suppose we take G, multiply, here I should mention that I'm going to consider only abelian groups, right? Otherwise this would be more complicated. So we construct this quotient, and then we multiply by this symplectic normal space or symplectic slice. Now here, the isotropy group GZ acts on these three spaces. Here it will act on the right. Here it will act by diagonal action on the left. So you can form this principal bundle. You can see this also as an associated bundle, but I prefer to look at it as a principal bundle. And this thing is a local model for your symplectic manifold or phase space around your point Z, in the sense that this particular point, the class of E00, is mapped to Z. Now, I will call this phi. We can do the following. We can take the Hamiltonian function, which lives on P, and pull it back by this phi, and what we are going to get is a function here. But this function is going to be G invariant, because the original function here is. So it will no longer depend on G. It will depend only on this factor and this factor. So this is going to be a function that I call H bar, which belongs to this product. It's a function on this product, and it's Z invariant. Why? Because it's coming from descending this function from here to here. It's our way. Okay, so the idea is to substitute our Hamiltonian system on P by some flow, local flow, on this space, and then study what happens here and recover the information by going back with this map phi to the original model, the original space. That's the idea of the tube equations. So the idea is you pull back Hamilton's equations by phi, so you have a flow here, and then you lift it to this space, which is not a quotient, and it's simpler, it's just three-way product. Right? Now, this problem has been studied since the beginning of the 90s, I believe, and has been studied by Esmeralda Sousa Diaz, Mark Roberts, Claudia Wolf, Jeroen Lamb, Juan Pablo Ortega, and Tudor Ratio. And what they do is they give the precise differential equations for one particular lift of this process. So they choose to pull back the Hamiltonian vector field from here to here, and then give the differential equations for one lift, one special choice of the lift. And these equations are the following. So this is on G, this is on G times GZ star, and this is on N. Now, when you study linearization of symmetric Hamiltonian systems along a relative equilibrium, for some technical reasons, what you do is to linearize this. I don't want to enter into this, but relative equilibria are solutions which are along the group orbit, so you want to linearize in directions transversal to this group. But also, because of Noether's theorem, momentum should be conserved, so you don't want to linearize in these directions, which are basically transversal to the symplectic leaves of the Poisson-reduced space. Anyhow, this is, of course, they don't write it in this way in these articles from 19th or before, but basically this is what is happening, right, in more modern terms. Now, I mentioned before that it's important to notice that what they do in solving this problem and writing these tube equations is choosing one particular lift. Now, the idea that James and I want to sell is very simple, and the only thing is that instead of looking to a particular lift, you should look at all possible lifts. And how do you go from this particular lift to all possible lifts? Very simple, you simply add all vertical directions or all vertical vector fields to this projection pi. And doing this is you choose an element eta in the Lie algebra of your isotropy group, GZ, and then you add the vertical directions, which I'm going to show here how they are, G eta. Here you add star eta rho, and here you can compute this is right. This is this blue part corresponds to the infinitesimal generators of the GZ axiom in this product space, which are vertical with respect to this projection. Now, instead of linearizing this particular choice of the lifted flow, you could look at the linearizations for any of the lifted flows. And if you do this, things look very differently, as I'm going to show now. Let me see. Have 10 minutes, maybe? Yeah? 10. Okay. So, let me see how I'm doing. Okay. Now, just a matter of notation. If we look at all possible linearizations depending on this free parameter eta, which is the Lie algebra of the isotropy group, I call this the full linearization. That is what I'm going to show now here. Okay. So, if we do this linearization is given by this expression where A, B, and C, as you see, depend on both lambda, the physical parameters of the problem, and this free parameter eta. And we can compute the eigenvalues, which are given by this expression. One thing they want to notice is that this F could be positive or negative exactly depending on the fast top condition. So if F is positive, it's exactly when the top is stable, and if it's negative, it's exactly when the top is unstable. However, this other parameter includes the freedom in eta, meaning that depending on which linearization I choose, I will see different eigenvalues. Then, we can look at what is happening in the oblate case. In the oblate case, if we move along the horizontal line, which is lambda, the family of the sleeping Lagrange stuff, this yellow part corresponds to lambda before the fast condition, meaning that the top is unstable. And of course, you observe that you have a quadruple with a non-zero real part. Now, forget about this blue line. I'm not going to use it. Here, if you choose at each point the linearization corresponding to the free parameter eta being equal to lambda over 2, which I said before is what they implicitly are doing in the Lewis et al. Paper, what you are doing is following this line, right? Instead of being in this two-dimensional case, you are only following this line and seeing what is happening to the eigenvalues. When you cross the fast condition, of course, this quadruple belongs only to the real imaginary axis, to the imaginary axis, and then it continues doing so, but at this point, so this line, this curve is hyperbola, and this is precisely the cases where I can make E in such a way that I cancel with F and I get a zero eigenvalue. I can get a zero eigenvalue for every point for which F is positive. That means in the stable range of the Lagrange stop, right? But if you follow this line, you only see it at this point, when the green light that you are following crosses this hyperbola. And this is the point that they identify with the fast superfast transition. But of course, if instead of following this line, you choose a different way, you can find this crossing for any point of the stable range, meaning that the fast superfast transition actually happens for every point in the stable range. Now, as I mentioned before, they observed, or they saw this transition only in the oblate case, which is the one I picture here. Why? It's going to be clear in the following slide for the prolate case, where this hyperbola now, that is precisely where you can find two eigenvalues being zero, does not meet this choice of gauge, if you like, this choice that they do implicitly in this paper. So in the prolate case, they can never see this behavior. However, it exists if you just choose to linearize in a different way, which is also valid. So exactly, again, as in the prolate case, this shows that there is no special difference between prolate and oblate cases, and you can find fast superfast transitions in each point of the stable range of the sleeping Lagrange stops. What is this telling us? Actually, when you do this, there is a crossing of eigenvalues, and there is actually bifurcation. There is a bifurcation of the sleeping Lagrange stop to the precessing Lagrange stop that we know happen in every point of the stable range. And if you choose how to linearize, actually you can see this bifurcation or this crossing of eigenvalues happening at each point in the stable range. Only that if you choose this particular choice of parameter eta, you will see it only at this point, that you will think that it's special, but it's not. So there is no special difference between the oblate and prolate case. And this crossing happens at every point of the stable range, and actually is a reflection, or is an indication of the bifurcation that happens from the sleeping Lagrange stop to the precessing Lagrange stop. And I think I'm done with time. Thank you very much.